these forces go through a bigger distance than just the short distance between the atoms. What it is if you have charges like electrons that are both the same. They repel each other with a force. They're little tiny particles. They're a piece of the atom, and they repel each other with a force which is enormous. It's inversely as the square of the distance, just like gravity is inversely as the square of the distance, but gravity is attractive, and this is repulsive. And for two electrons, the gravity is so weak compared to the electricity. Electricity is so much more enormous than the gravity. I can't express it because I don't know the name of the number. It's 1 with 30 or 8 or 40 zeros after the 1. Bigger is electricity. It's so enormous that if I were all electrons, well, the numbers are too big. So if there's also, however, for electrical things, other kind of charge, positive charges. An example of protons are positive. They're inside the nucleus of the atom, and they attract electrons. Opposite charges attracted, like charges repel. So you have to imagine enormous forces where likes are trying to get away from likes, and unlikes are trying to get near the opposite. What would happen if you had a lot of them? There'd be, all the likes would collect with unlikes. They attract each other. And they'd get an intimate mixture of pluses and minuses all on top of each other, very close together. You wouldn't have a lot of pluses anywhere because they repel each other. They'll all be compensated by minuses very close. And you get these little knots of plus and minus. The reason that the knots don't get smaller and smaller is because they are particles, and there's quantum mechanical effects that we won't discuss that makes it that you can't get any smaller than a certain size. And so you get these little lumps, which are balls. They're the atoms. The atoms have positive and negative charge, and they're neutralized. They cancel their charge as nearly as they can. And because of this force is so big, it ends up nowhere, with very little left. Because it's so big, it cancels out. There's always so exactly the same pluses and minuses in any normal material. When you comb your hair, it rubs just a little bit extra, or just a few extra minuses, say, here, and somewhere else a few extra pluses. But the forces are so big, there's just the extra ones which make a force that we can see that seems to be at a long range. And that we find mysterious, and that we need an explanation for. And we try to find an explanation for it in terms of ideas like the forces that are inside of rubber bands or steel bars or twisted things. We would like to have some kind of puller at a distance because we're used to it, that we don't get any push until we're touching. But the fact is that the reason we don't get any push until we're touching is it's the same force as you see at a long distance, only it's come down to short because the pluses and minuses have canceled out so well that you don't feel anything until it gets very, very close. When it gets close enough, of course, it makes a difference which is plus and which is minus and where they are, and they repel each other. So it's kind of fun to imagine this intimate mixture of highly attractive opposites, which is so strong that they cancel out the effects. And it's only sometimes, when you have an excess of one kind and another, that you get this mysterious electrical force.